So what's a derivative good for? Derivatives are good because they can give you the instantaneous rate of change of a function. And we care about that in physics because if your function happens to be, say, the position function, in other words, say you had the position as a function of time, maybe the position of some object, a squirrel, is like 4 times t, or maybe it's like 3t squared, or maybe it's 4 sine of 2t, or something more exotic like 6e to the negative 3t. If you know what the position is as a function of time, then you can take a derivative of that position and it gives you the instantaneous rate of change in the position, and we already have a name for that. That's called the velocity, and we like velocity. We're interested in velocity in physics. That's why we're interested in derivatives. But it doesn't stop there. One derivative of position gives you velocity, but you can take another derivative of that velocity and you get the instantaneous rate of change of the velocity, which is going to be the acceleration. And we care about acceleration too in physics, so it's another reason why we care about derivatives. So you could keep taking these derivatives, you keep getting variables, you can give different names, and as you keep doing it, what you're really doing, so if over here I could write this like this, I could write this as derivative with respect to time of, well, of v. And what is v? V is the derivative with respect to time, whoa, that got ugly, with respect to time of x. And so this is kind of ugly. It's like ddt, x. There's a shorthand for this. If you take 2 derivatives with respect to time, a shorthand for that, so it doesn't take up so much space, is d squared dt squared of x. But I mean, this is really just shorthand for that. It means nothing more or less than 2 derivatives back to back, both operating on some position function. What does that mean? Let's find out. Let me get rid of all this. And if you haven't taken calculus, this may look like mathematical witchcraft coming up. You may want to refer to the calculus videos that show you how to do a derivative at Khan Academy. But if you want to hang around for the ride, feel free. You can kind of get a feel for what these things do just by watching some examples. So let's say you had a position as a function of time. Let's say it was 4 times t. So let's say this was a squirrel, and this means its position at t equals 0 would be 0, and its position at t equals 1 would be 4, and its position at t time equals 2 seconds would be 8 meters, and so on. And you wanted to know what's the velocity as a function of time for this squirrel? Well, you can just take a derivative. So I'm taking this whole function right here. I'm just going to copy that, put that down right here. Where the x was, I'm just going to replace it with my function for x, and my function for x for this particular squirrel is 4 times t. So if I have 4t as my function, I take a derivative of it. What am I going to get? Well, I can pull the 4 out. First rule with derivatives, if you got a constant, you bring that out front and it doesn't get affected. So I have d dt of just t now. And this is really the power rule. If you want to think about it, if you have, we're going to use this over and over, if you have derivative with respect to time of some t to the power n, that's always going to equal n. You pull the n down, this exponent down, times t to the n minus 1. If you haven't seen this derived, this is at this point is just a statement I'm making, but this is true. This is how you take the derivative of some power of a variable, and this comes up a lot in physics. So what we're going to do over here, we're going to say that t is really t to the 1. So I can pull down the 1, and I get 4 times 1, which is just 4. And then t to the 1 minus 1 is 0. I could write this as t to the 0, but that's kind of stupid because t to the 0 is just 1. So we just write this as 4. In other words, the velocity as a function of time isn't really a function of time at all. It's just 4. So this squirrel has a velocity of 4 meters per second, and it's just a constant 4 meters per second. And then if we want to get the acceleration, we take this function we just found, 4, and we bring it over to here, and we plug it into our velocity, and we say that a derivative of that velocity function, which is 4, will give us the acceleration, except the derivative of a constant is 0. This is giving us the rate of change of this thing in here, and 4 is just 4. 4 has always been 4, and it will never be anything besides 4. 4 hasn't changed ever since people invented the idea of 4. So the derivative of 4 is just 0. There's no change in the number 4. Only if this velocity function had some function of time in it, if there was a t in here, a t squared, then your acceleration would be non-trivial, i.e. not just 0. So let's look at another example. Let's see what happens here. Let's get rid of all this, and we'll say that our function instead is 3t squared. So what would my velocity be if this squirrel had a position function of 3t squared? So I'm going to take the derivative of that function with respect to time, 3t squared, and I get to pull the 3 out because it's a constant, and that's just a rule of derivatives. Hopefully this isn't looking like mathematical witchcraft. Again, if this doesn't seem right, go watch the calculus videos on taking derivatives, so this makes sense. I'm just assuming you've seen that. And if I take a derivative of what's left here, which is t squared, I'm going to get, all right, power rule. I pull the n down, the exponent down, which is 2, so 2 times 3 is 6. And then what I'm left with up here, 2 minus 1, I always subtract 1 from the exponent. 2 minus 1 is 1, and t to the 1, t to the power 1 is just t. So I get 6 times t is my velocity as a function of time. Now if I want my acceleration, I take one more derivative. I take the derivative of this velocity. So the derivative with respect to time of 6 times t is again a power rule. I pull the 6 out. I get 6 times the derivative with respect to time of t, which we already said is just 1. So the derivative of t with respect to time is 1. So my acceleration of this squirrel is a constant 6 meters per second squared if this original function was in meters. Usually we leave off the units when it's symbolic, otherwise this unit looks like it might be one of the variables, but it's really just a unit. So let's look at another example. Let's say you had something more exotic. Let's say instead of that you had a position that was 4 sine of 2t. So this squirrel's moving back and forth like a sine does, and if I wanted the velocity of this squirrel, I'd take the derivative of its position function. So the derivative of 4 sine of 2t, well, I've got a 4 out front, that's a constant, that gets to come out front, so 4 times the derivative with respect to time of sine of 2t. So I take the derivative of this sine, and the derivative of sine, if you've never seen the derivative of sine, it turns out that it's cosine. So that's proven in the calculus videos on derivatives. So if you've seen that, you know that the derivative of sine is just cosine, so I'm going to get 4 times cosine, but I've got a problem. This in here isn't just sine of t. So it's not just sine of the variable we're taking the derivative with respect to, it's sine of 2 times the variable that we're taking a derivative with respect to. So what do you do in that case? It's called the chain rule. It's not hard. You first take a derivative of your function as if the thing in the argument was just the variable you're taking a derivative with respect to. So first we pretend like the only thing in this 2t is just t, and you take a derivative, and that's just cosine of whatever's in here. So I take the derivative of sine is just cosine, and then I leave the 2t in here as if I don't have to do anything to it. And it's called the chain rule, because the next thing you have to do if you're going to play that game, you then have to take a derivative of the inside. So then you say, okay, this wasn't actually t in here, it was 2t. So then you take a derivative of the inside, and the derivative of 2 times t, like we've seen, you can use the power rule, that's just going to be 2, because the derivative of t is just 1. And you multiply that function you've got by the derivative of the inside, this argument here, which is 2, and so I can just write this as times 2, but 4 times 2 is 8. So my velocity as a function of time is 8 cosine 2t. You might be like, whoa, hold on, what does that mean? Well, it means the velocity at any moment in time, just like those previous functions that I found. The velocity at any moment in time, t, is this. So if I wanted to know the velocity at, let's say, 3 seconds, I would plug in 3 seconds for time here, which means I'm plugging in 3 seconds for time here. I'd evaluate this function. I'd take 8 times cosine of 6, because 2 times 3 is 6. And whatever that comes out to be, that would be the velocity at that moment. Or if you leave it general in terms of t, it's basically giving you the velocity at any moment in time, whatever time you plug in here. And then you can keep going. I can find the acceleration by taking one more derivative. So I take that velocity function, which is the derivative of the position function, and I take the derivative of it, which is 8 cosine of 2t. So if I take the derivative of this, the 8 comes out front because it's a constant. And the derivative of cosine is negative sine. So I'm going to get a negative sine. Oh, haha, negative SIGN sine, that is. And then I also get SIN sine. Sorry about that. So the derivative of cosine is negative sine, which means I get a negative sine on my 8, and I get the sine here, times 2t. Again, I've got to use the chain rule. This wasn't just t in here, so I have to take one more derivative, and the derivative of 2t is 2, which means I'd have negative 8 times 2, which is really just negative 16. And this would be the acceleration as a function of time. I plug in whatever time I want, 3 seconds, 7 seconds, in for my t. I evaluate this function and it gives me the acceleration at that particular moment in time. So we'll look at one more. Let's say it was really crazy, some negative exponential. What do we do now? Well, if we want the velocity, we do the same thing. We take a derivative with respect to time. So I'm going to take the derivative of my position with respect to time, and I get to bring the 6 out, so I have 6 times d dt of e to the negative 3t. Again, it's a chain rule. I know what the derivative of e to the t is. It's just e to the t. So first I pretend like negative 3t is just t, and I say that this is 6 times e to the whatever's up here, as if I didn't have to mess with it. But I only get to do that with the chain rule by then multiplying what I get by the derivative of this function up here that we're raising e to the power of. So now, just like with my sine and cosine, I take the derivative of the argument up here, which is negative 3t, and the derivative of negative 3t with respect to t would just be negative 3, because the derivative of t with respect to t is just 1. So I get times negative 3, and 6 times negative 3 is just going to be negative 18. This would be my velocity of this squirrel as a function of time. And if I wanted the acceleration as a function of time, I would then take a derivative with respect to time of my velocity. And we just found that. That was negative 18 e to the negative 3t. And I take that derivative, I get to bring the negative 18 out. I get negative 18 derivative d dt of e to the negative 3t. And again, we just saw what that was. The derivative of e to the negative 3t is e to the negative 3t times a negative 3, because you have to take a derivative of the top. So I get a negative 3 times a negative 18 is a positive 54. E to the negative 3t would be my acceleration as a function of time of this squirrel. Whew. So that was four quick examples of how you could use position to get velocity, and how you can then use velocity to get acceleration by using derivatives, which would then give you the velocity as a function of time and the acceleration as a function of time at any time t that you plug in to these functions.